So here we are, we're in chapter 8, we're looking at periodic properties of the elements. This is going to be critical for the last three chapters, chapters 8, 9, 10, and 11, so I guess that's 4 chapters, moving forward. So we look at section 8.6. The idea here, that the big one is called effective nuclear charge, but even more importantly is this idea of Coulomb's law. And I want to be very clear about this. Anytime on the AP test, or anytime I ask you to explain kind of why something is occurring the way that it is, this is the level you need to bring it to. You want to break things down to Coulomb's law. You want to break things down to effective nuclear charge. They are really Coulomb's effective nuclear charge uses Coulomb's law. That's the level you need to bring this to. So here's the basic idea here. Because electrons have a negative charge, they will be attracted to the nuclei, which is positive charge because positive and negatives attract. We know that already. Now, many properties of the atom depend not only on their electron configurations like we saw previously, but also on how strongly those outermost electrons will be attracted to the nucleus. What Coulomb's law tells us, it is a mathematical equation, but we don't need to know the equation, we need to know the idea of it. Coulomb's law tells us that the strength of this attraction between the nucleus and the outer electrons depends upon the signs, positive versus negative, and the magnitude, the amount of charges, as well as the distance between them. Think of this like playing with magnets. There's a magnetic kind of correlation of Coulomb's law, that if I take two north ends of a magnet, they're going to repel each other. The stronger the magnets are, the stronger they're going to repel. The closer they are, the stronger they're going to repel. Pretty much the exact same thing, but with charges. If I have two positive charges, they're going to repel. The stronger the positive charges are, the more they're going to repel. The closer those positive charges are, the more they're going to repel. Same idea. Thus, the force of attraction between an electron and a nucleus, so now we're talking a positive and a negative, depends upon how much charge is acting on the electron. Again, that's the amount of charge. We know it's going to be an attractive force because positive and negatives attract, and the average distance between the nucleus and the electron. And what we know is that the closer the distance, the stronger the attraction. So this force of attraction increases as the nuclear charge goes up because the charge on any given electron is the same. So more charge from the nucleus means stronger attraction. Closer to the nucleus means stronger attraction as well. Now, where this gets complicated is when we have a many electron atom, so anything but hydrogen. Because what's going to happen is each electron is simultaneously attracted to the nucleus, positive versus negative, but also repelled by the other electrons, negative to negative. Generally, there are so many electron-electron repulsions that we cannot analyze the system or situation exactly. But we can do kind of an average in general sort of situation. So again, we can estimate the net attraction of each electron to the nucleus by looking at how the electron interacts with its average environment. And that means the environment created by the positive charge from the nucleus, so that attraction, but also the repellent force of those electron-electron repulsions. So to do this, we use this idea called effective nuclear charge. Now, by looking at the average situation, we can treat each electron individually. So we're kind of pretending that each electron is isolated and it's moving in a net electrical field created from the positive charge of the nucleus and the negative charge from the other electrons. And what we're pretending is this whole situation of attraction to the nucleus and electron-electron repulsion is as if it results from there being a single positive charge located at the nucleus. We call that charge the effective nuclear charge. Now that's different from the actual nuclear charge. The actual nuclear charge is just the number of protons, because that's the positive charge of the nucleus. We're talking the effective nuclear charge. That's the whole situation altogether. Now, the effective nuclear charge of an electron will be less than the actual because we not only have that attraction to the nucleus, which would be the actual, but also we have to take into consideration that attraction to the nucleus is diminished from the electron-electron repulsions. So if Z would be the actual nuclear charge, this number of protons, the effective nuclear charge is less than the actual. How do we estimate the effective nuclear charge? So a valence electron, again, that's an outer shell electron, is attracted to the nucleus, but again is repelled by other electrons. Now, in particular, it turns out that the electron density that is due to the inner electrons are very effective at partially canceling the attraction of any valence electron to the nucleus. So what this means is that valence electrons don't really care about other valence electrons. That repulsion is so minimal we don't worry about it. What we do concern ourselves with is any of the inner electrons. So we say that these inner electrons partially shield or screen the outer electrons from the attraction to the nucleus. We can write a relationship between effective nuclear charge and the number of protons. So effective nuclear charge equals the nuclear charge, that's just the number of protons, minus S. What is S? I hear you ask. Well, it's not entropy in this case. We just run out of variables. S is something called the screening constant. And what S represents is how much the inner electrons shield the valence electrons from the nucleus. What we're going to assume is that S is usually pretty darn close to the number of core electrons in an atom. The inner electrons, the not valence electrons. And by usually close to, it means when we are talking an estimated effective nuclear charge, S will be equal to the number of core electrons in an atom. Again, valence electrons don't shield each other, only the core electrons shield. So, talking expected effective nuclear charge values. So, what would we expect the effective nuclear charge of sodium to be? So, looking at a periodic table, I see there's the electron configuration for sodium. Sodium has 11 protons, so its Z would be 11. We would expect the S to be 10 because there's 10 inner electrons. You can always think of the noble gas that comes before, so that neon has 10 electrons. Everything in period 3 would have an S of 10. So the effective nuclear charge would be plus 1. That's what it is. Now, is that what the effective nuclear charge actually is? No. If you remember from the last chapter, there's actually the 3s orbital has a small chance of being closer to the nucleus than where it normally is. So there's a small chance of the 3s electron will be closer, kind of avoiding some of those inner electrons, giving greater attraction. So the effective nuclear charge is actually slightly higher than the estimated, but you don't need to worry about that. Now, this effective nuclear charge explains the energy amounts for the different L values within the same energy level. Again, L values would be the sublevels. So the 2s sublevel has a greater probability to be closer to the nucleus than the 2p, even though they're part of the same energy level. This means because the 2s is closer, that means that there's a slightly greater attractive force between the nucleus and the 2s electrons. That greater attraction means lower energy. And the bell just went off, which means nothing for any of you. And this rule applies to all the energy differences between sublevels. Now, trends in effective nuclear charge for valence electrons. So, the effective nuclear charge, as we move across the row, it increases. That's because the number of core electrons remain the same. Again, every element in period 3 has 10 core electrons, but the total nuclear charge goes up, so that means Z increases, but S remains the same, so effective nuclear charge increases. Going down a column or family, the effective nuclear charge changes much less than moving across. The expected effective nuclear charge should stay the same, but we actually see a slight increase in effective nuclear charge as we move down a family, but again, you don't have to worry about that. Again, if you are just talking general expectations, within a family, effective nuclear charge should be the same. Now, periodic trends in the size of atoms. So now that we have this, let's talk size of atoms. Now, an important property of atoms or ions is their size. But again, we can't think of an atom or ion as a hard spherical object because there's no sharply defined boundaries where the electrons are and then aren't. It's all fuzzy. but we can still define an atom size in several ways based upon the distance between individual atoms in different situations. So how do we do this? So imagine a bunch of argon atoms at room temperature. I say argon because it's a noble gas, so it's a monatomic element. When they collide with each other, they ricochet apart like pool balls. Now this happens because the electron clouds of each atom can't penetrate the other atom. Electrons and electrons repel. The closest distance the nuclei get during such a collision determines the apparent radii of the argon atoms. We call that the non-binding atomic radius because it's what we see when there's not a bond. Now imagine a chlorine molecule, Cl2. The chemical bond holds the chlorine atoms to each other. So this attractive interaction brings the atoms closer than they would be in a non-binding collision. So we call that radius the bonding atomic radius, and it's going to be shorter than the non-binding atomic radius. And again, chemists use different methods to measure the distance separating nuclei. So for instance, in the iodine molecule, the distance separating the nuclei is found to be 2.66 angstroms. An angstrom is 10 to the negative 10th meters. We find the bonding atomic radius to be 1/2 the bond distance, so 1.33. And again, that's what we generally see, that the bonding atomic radius is half that of the non-binding radius. It's just what it is. Here is a chart showing general radii for different elements, and we can see general trends moving left to right. And from top to bottom, we can see going from top to bottom, atoms get larger. From left to right, generally they get smaller, with, again, weirdness happening here in the noble gas region because that's where weirdness happens. So, periodic trends. Now, again, for each of these, you need to know the trend and you need to know the why. And for the why, we want to break it down to effective nuclear charge and Coulomb's law. So within each family, or atomic column or family, the atomic radius tends to increase as we go down. The big reason for this is the increase in the principal quantum number. There's more energy levels. And that means electrons have a greater probability of being farther from the nucleus, which makes it larger. Within each row or period, the atomic radius tends to decrease from left to right. This is because, again, as we go from left to right through a row or period, the effective nuclear charge goes up. That means the electrons are more attracted to that nucleus. And because they're more attracted, they're going to move closer, causing the atomic radius to be smaller. So now we're on 8.7, periodic trends in ionic radii. So the radii of ions is based upon the distance between the ions in ionic compounds. So it's kind of like the bonding radii. So like the size of an atom, the size of an ion depends on its nuclear charge, the number of electrons it has, and the orbitals in which those valence electrons are found. So for cations, so again, for the formation of a cation, we're going to empty the larger occupied orbitals in an atom, which will, we're emptying an orbital, so it's going to get smaller, and we're also decreasing the number of electron-electron repulsions, all of which causes the cations to be smaller than their parent. Anions are kind of the opposite. The formation of an anion begins to fill up the larger occupied orbitals. And we're going to increase the number of electron-electron repulsions because there's more electron-electron repulsions. The electrons spread out more, making it larger than the parent atom. Now, for ions with the same charge, size increases as you go down a column. And that's what we see here. So everything in the color is the size. So we can see cations or anions, cations in pink, anions in blue. As we go down, ions get larger. And again, that's still because we have more energy levels. But from left to right is that trend that we see. So again, we get smaller, then smaller, then smaller, and again, smaller, then smaller as we go from left to right. But again, when we look at the anions versus the cations there, the anions are much larger because, again, we're increasing the number of electron-electron repulsions. Now, isoelectric ions. So, fancy term for something pretty darn simple. An isoelectric series is a group of ions that have the same number of electrons, not valence electrons, total electrons. So, for instance, oxide ion, fluoride ion, sodium, magnesium, and aluminum all have 10 electrons total. They would be an isoelectric series. Now, in any isoelectric series, if you list the members in order of increasing atomic number, When you do that, that means the radius of the ions decrease throughout that. So listing these in increasing atomic number, excuse me, would be oxide, fluoride, sodium, magnesium, aluminum. So oxide would be the biggest, and we would expect aluminum to be the smallest. So this is a way to actually compare anions and cations and even different elements in different periods. This leads us to ionization energy. So ionization energy is all about the ease of which electrons are removed from an atom or ion, and how easily that happens has a major effect on chemical behavior. So ionization energy is how much energy is needed to remove an electron from the ground state of a gaseous atom or ion. Now the first ionization energy, or I1, is the energy needed to remove the first electron from a neutral atom. So it was neutral, now it's no longer. So here's sodium, we now have a sodium ion and an electron. The amount of energy needed to do that would be called the first ionization energy. The second ionization energy, or I2, is the minimum energy needed to remove the second electron from an ion that has already lost one. So it's not the energy needed to remove 2 electrons, it's the energy needed to remove a second electron. So you've already paid the first ionization energy. Then if you pay the second ionization energy, you can remove a second. So you can see here we're starting with the sodium ion, and now we have a sodium 2+ ion. Now, the greater the ionization energy is, the more difficult it is to remove that electron. That's the energy cost to remove that electron. Now, variations in successive ionization energies. As successive electrons are removed from an atom, the ionization energy increases. So that means I2 is always bigger than I1. I3 is bigger than I2, so on and so forth. Just that. And that's because it's harder to pull an electron away from more positive and positive ion. So again, first ionization energy is removing an electron from a neutral atom. Second ionization energy, you now have a cation, and you're trying to remove an electron negatively charged from something that's positive. That's harder to do. The more positive it is, the more electrons it's been removed, the harder it is to remove another. Now, there is a huge jump in ionization energy once you try to remove an inner shell electron. So again, there's an increase for removing valence electrons, but as soon as you try to remove an inner core electron, an inner electron, now the ionization energy jumps up incredibly. For instance, silicon. Silicon, if we look at the periodic table, has four valence electrons. So that's what we see there. So if we remove all the 3s and the 3p, those are the valence electrons. I1 is 786 kilojoules per mole. We'll just ignore and pretend that that extra kilojoules isn't there. Hey, look, it's gone. We can see I4 being 4,360. Again, that makes sense. Higher ionization energy, bigger jump. So we see a pretty significant jump between I1 and I4. But I5, notice, is hugely different because now we're trying to remove an inner core electron because silicon only had 4 valence electrons. Once you try to remove something that's not a valence electron, it is really, really, really hard. So this is a way of telling you kind of how many valence electrons an atom has. So if we weren't told that it's silicon, so let's say we weren't told it's silicon, we weren't told this, but we see this information, we see that huge jump between the 4th and the 5th ionization energy, that tells me that 4th electron was the last valence electron. That 5th one, we are now digging into the inner core. And again, the big reason for it is, again, the second energy, you're trying to remove a 2p electron at that point, they're much closer to the nucleus than the 4 third energy level electrons. And because the 2p is closer, it's going to experience a greater effective nuclear charge. Smaller distance means greater attraction. And for the 2p electrons, or the second energy level electrons, there's fewer inner electrons for that. So again, higher effective nuclear charge, more attraction. So again, every element shows a large increase in ionization energy when electrons are removed from its noble gas core. And again, this lends support to the idea that only the outermost electrons beyond the noble gas core are involved in bonding, because trying to remove an inner electron is such a huge cost in energy. And again, those inner electrons are just too tightly bound to the nucleus to be lost or even shared with another atom. So, periodic trends and first ionization energies. Within each row or period, the first ionization energy will generally increase with increasing atomic number. So again, alkaline metal should be the lowest, a noble gas is the highest. This should make sense because again, as we move from left to right, effective nuclear charge goes up. Those electrons are more tightly bound to the nucleus. That's what Coulomb's law tells us. Higher charge, more attraction, so harder to remove. Within each column or group, the ionization energy generally decreases with increasing atomic number. So as we move down a group, again, atoms get larger. Because they're larger, the electrons are farther from the nucleus. And because they're farther from the nucleus, the effective nuclear charge, Coulomb's law tells us, or nuclear charge stays the same. Effective nuclear charge stays the same, but it's greater distance. Greater distance from Coulomb's law means less attraction, easier to remove. The representative elements show a larger range of values of I1 than the transition metals. Transition metals break our rules. Generally, transition metals increase slowly as we go from left to right within a period. F block is a very, very, very small increase. Don't worry about those at all. And again, this is what we see for generally the representative elements. And again, that's what we see from left to right, generally increasing. Few dips here and there, and we can kind of talk about that, but not that critical. So again, in general, smaller atoms have higher ionization energies. That's because the same factors that affect atomic size influence ionization energy. It gets about that attraction to the nucleus. Again, the energies needed to remove an electron from the outermost shell depends upon the effective nuclear charge and the distance from the nucleus. So again, as effective nuclear charge goes up, ionization energies go up. Now again, there are occasional irregularities, and this is explained by energy levels. Higher energy level generally equals lower ionization energies. So this then leads us to the electron configuration of ions. When electrons are removed from an atom to form a cation, they will always come from the orbitals of the highest energy level first. Don't overthink this statement, accept it as true. Highest energy level first, not highest energy subshell. Highest energy level. For example, with iron, to go from iron to iron 2+, we're going from, here's the electron configuration of iron, here's the electron configuration of iron 2+. Notice we lost the 4s. Even though 3d is technically higher in energy than the 4s, we lose the highest energy level electrons first. If we removed a third electron, then we'd remove it from the 3d, and it would be argon 3d5. So here we are in section 8.8. We're looking at electron affinities. This can really be seen as kind of the opposite in idea, not number, but opposite in idea to ionization energy. So again, the first ionization energy of an atom is, again, how much energy it needs to remove one electron from the atom. And we see this is what we saw in the last section, no great surprise there. And again, the positive value means that energy must be put into the atom to remove the electron. Now, many atoms gain electrons to form negatively charged ions. It's not always just removal of electrons, there can be gaining of electrons. There's an energy change associated with when an electron is added to an atom, and we call that electron affinity. So again, it's kind of the opposite in idea, not value, but idea of ionization energy. And what it's doing is it's measuring the attraction or affinity for the atom to gain an electron. Now, for a lot of atoms, energy will be released when electrons are added, making it a negative number. So for instance, with chlorine here, with chlorine atoms taking an electron to form chloride, we see energy change of negative 349, very, very common. So when that chlorine becomes chloride, it actually gives off energy. It becomes more stable that way. Now again, they are not the same thing. Ionization energy measures the ease at which an atom loses an electron. Electron affinity measures the ease at which an atom gains an electron. And again, it's not just one's the negative of the other. They are two separate values. Now, the greater the attraction between a given atom and that added electron, the more negative the electron affinity is. And this is where we have to be a little bit careful with our terminology. So when we talk a high electron affinity, what that's going to translate to is a large negative number. The more large and the more negative the number is, the larger the electron affinity is. That's just how we describe it. Now, for some elements like noble gases, the electron affinity actually has a positive value, which again means very, very low electron affinity. It means that the anion is actually higher in energy than the separated, and again, things want to be low in energy. So here's a general chart of electron affinities for different elements, and there's some oddness here. There's definitely some oddness, and we're going to address in the notes. So the general trends is that the halogens will tend to have the highest electron affinity. In general, we tend to see electron affinity increase as we go from left to right, maximizing in the halogens. And that's because with a halogen, gaining one electron gives them that stable noble gas configuration. Now we see that the electron affinities of noble gases and things like beryllium and magnesium are actually positive, which means very, very low electron affinities. And that's because as we add electrons to them, we're actually going to start filling up a currently empty higher energy subshell. With like beryllium, we see, so beryllium would end with 2s2. Adding one electron, we're now putting an electron into the 2p, which was previously empty. And so that takes actually a lot of energy being put in to start filling up a higher energy subshell. Now there's a few interesting notes here, like nitrogen, phosphorus, arsenic, tin there. Not tin, antimony, my apologies. Now that added electron, so these are nonmetals. We normally, again, or metalloids, that added electron, again, normally we see nonmetals having a relatively good electron affinity. They form anions. We know this. But what's happening with that, so if I look at nitrogen, take a look at a periodic table. So nitrogen's electron configuration would end with 2p3. So that means each of the 2p orbitals has one electron in it. By adding one more, we're actually increasing electron-electron repulsion because we're now going to be doubling up electrons within an orbital. And that actually creates that weird little dip in electron affinity. So, like oddly, nitrogen has a lower electron affinity than carbon because of that. Now, as we move down a group, electron affinity really doesn't change greatly. And that's because although there's less electron-electron repulsion because everything's more spaced out, also the distance to the nucleus is greater, which means that there's lower electron nucleus attraction, and the two factors kind of balance each other out. Now again, one thing I want to stress, you do not have to know those weird little dips like nitrogen, but if the AP people show you that data and ask you to explain it, that you need to be able to do. And here we are in 8.9. So now we're just going to do kind of a collection of some general properties of these groups. So again, we know elements can be broadly grouped into categories of metals, nonmetals, metalloids. Hey, look, everything in blue there is a nonmetal. The purple is the metalloids. The kind of grayish beige color is the metals. Again, most elements are metals. They're found on the left and middle portion. We know this. Nonmetals are found in the top right. We know this, I hope. And metalloids are in between. Metals, they're shiny, they have luster, they conduct heat and electricity, they're malleable, all except mercury are solid at room temperature. I'm moving fast to this because hopefully this is not a revelation to you. They tend to have low ionization energies, which means because they tend to form cations relatively easily. So that means electrons need to be removed without too much difficulty. We often characterize them as an oxidizer because they tend to lose electrons during a chemical reaction. But don't worry about that. Metals and others, compounds of metals with nonmetals tend to be ionic. We oftentimes produce things called oxides, which is a metal with an oxygen, so nickel 2 oxide, sodium oxide, things like that. Most metal oxides are basic because when they dissolve in water, they actually react with the water to form metal hydroxides, which again, that hydroxide piece is then what's basic. So the metal hydroxides are really what's basic. So we say the metal oxides are basic, but it's really the step after them that's basic, but we kind of shortcut that. And the basicity of the metal oxides is due to that oxide piece. Now for nonmetals vary greatly in appearance. They are not lustrous. They are generally poor conductors of heat and electricity. They tend to have low melting points. Some have such low melting points they are gases by the time we get to room temperature. Seven of them exist as diatomics. You know your diatomics. They can be solids, liquids, or gases at room temperature. Chemical reactions, because they tend to have high electron affinities. Again, they tend to gain electrons when they react with metals. Compounds made entirely of nonmetals are molecular, and most nonmetal oxides are acidic. So again, you really just have to remember one, either metal oxides are basic, or remember nonmetal oxides are acidic. Either way works. And that means when they dissolve in water, they'll react to form acids. The way I always remember this is carbon dioxide. Carbon dioxide reacts with water to form carbonic acid. That's just something I know, and that kind of reminds me that the non-metal oxides, carbon dioxide, is acidic. That means that metal oxides are basic. Metalloids, again, they're in the middle, and they have properties somewhere between metals and nonmetals. So for example, silicon looks like a metal, but it's brittle and is a poor conductor of heat. And they kind of mix and match the properties of metals and nonmetals, depending on the compound that they're in. So some group trends, we're going to look at the chemistry of alkaline metals, alkaline earth metals. Again, this is stuff that is not super new, but I want to address. So group 1A, the alkaline metals, they tend to be very soft, very silvery, high thermal electrical conductivity. They actually come from the Arabic word meaning ashes, is where alkali comes from, because they were isolated from wood ashes by early chemists. They tend to be not very dense, have low melting points, and as we move down the group, the melting point actually decreases to the point, I think it's rubidium. I'm pretty sure it's rubidium. As you cut into it, actually the friction of cutting into it adds enough heat to cause it to melt. And again, that's why I say the melting point decreases as you move down, whereas the density increases as you move down. Since they have the lowest first ionization energy, they have electrons that are very easily removed. That means they're very reactive. They're so reactive they exist in nature only as compounds, and they will combine directly with most nonmetals pretty simply. They will react vigorously with water, producing hydrogen gas in a solution of an alkaline metal hydroxide. So in this case, M would be any of the alkaline metals. So we see this reaction, sodium being probably the most famous of these. So we get sodium plus water makes sodium hydroxide plus hydrogen gas. Very, very exothermic. It's so exothermic we normally talk that these explode when you put them into water. They themselves don't explode, but what happens is because they're producing hydrogen gas and they're exothermic, the hydrogen gas actually combusts, and it uses the exothermic reaction to kind of trigger that combustion. That's what I talk about there. It's more violent, not violet, violent with the lower alkaline metals since they more easily lose their electrons, more reactive. So as we go down, they're more and more reactive. Other reactions, when oxygen reacts with metals, metal oxides are formed, like lithium oxide here. And again, when dissolved in water and other soluble metals, they form those hydroxide ions. So again, metal oxides are basic. But other alkaline metals can react with oxygen to form metal peroxides, which contain the O2 negative. So example this. Peroxides are an issue because peroxide crystals are explosive. That's bad. Now what's interesting is potassium, rubidium, and cesium can also form superoxides. You don't need to worry about that. That's just kind of an FYI, kind of some neat chemistry. Again, generally we only worry about the oxide formation. Don't worry about peroxides or superoxides. Flame tests, although the alkaline metal ions are colorless, they each emit a color when you put them into flame. And as you put it into flame, it actually excites the electrons in there, and they give off light. Melting point, again, melting point decreases. We'll talk a little bit more about that when we hit chapter 11. Group 2A, the alkaline earth metals, they are solid at room temperature, typical metals. They tend to be harder, more dense, higher melting points. Their ionization energy is low still, but much higher than the alkaline metals, so much less reactive. Reactions, beryllium will not react with water. Magnesium won't react with liquid water, but will react with steam, and that's because of the higher energy to meet the higher activation energy requirement. And that's what we see there, forming that metal oxide, which would be basic. But calcium, strontium, barium, and radium will react with water, but still slower than the alkali metals. And again, same basic reaction. And again, in general, they tend to lose their two outermost electrons, form 2+ cations. Burning, they give off colors when you burn them. Good times. So group trends for selected nonmetals, hydrogen, because hydrogen has that electron configuration of 1s1, and we usually position it with the other alkali metals because they also end in something s1. But hydrogen really doesn't belong in any group. It's not an alkali metal because it's usually a colorless diatomic gas, but interestingly, under really high pressures, it acts more like a metal. Kind of interesting. Because there's no nuclear shielding of its sole electron, the ionization energy for hydrogen is quite high, and it's actually closer to the ionization energy for the things like oxygen or chlorine. It is much less likely to lose an electron than an alkali metal will. It tends to share its electrons and form molecular compounds. Reactions between hydrogen and nonmetals tend to be very exothermic. They react with metals to form metal hydrides, containing that hydride ion. And again, this property of hydrogen gaining electrons makes it more like a halogen than an alkali metal. So some periodic tables actually place hydrogen with the halogens because, like the halogens, if they gain one electron, they meet the octet rule, which is what it would be like helium. But hydrogen can lose its electron to form a cation, and again, we've dealt with this. This is the entire basis behind acid reactions. The oxygen group, so going down group 6A, we change from nonmetals to metals as we cross through the metalloids. So oxygen, sulfur, selenium are nonmetals, tellurium is a metalloid, polonium is a metal. All except oxygen are solid at room temperature. Two common forms of oxygen, normal molecular oxygen and ozone. Normal oxygen is much more stable, which is why we refer to O2 as just oxygen. These two forms are what we call an allotrope. An allotrope are different forms of the same element in the same state. Diamond and graphite would be allotropes. Sulfur, interestingly, the most stable form of a sulfur allotrope is S8. Even though that's the most common, sorry about that bathroom noise, I have my door open right now. Even though solid sulfur contains S8, we usually write it just as S to simplify the stoichiometry. So anytime we've done a reaction where we say there's sulfur as a reactant and we just wrote S, that's kind of a lie. It's really S8. Like oxygen, sulfur tends to gain electrons to form sulfides, which are S2 negative. Most sulfur in nature is actually in the form of metallic sulfides. Although less likely to form sulfides than oxygen is to form oxides, oxygen is more reactive. Group 7A, the halogens. Acetine is usually left out of this group. That's the AT at the bottom because it's so unstable and a lot of its properties just aren't well known. They are your typical nonmetals. They have pretty low melting and boiling points. Their melting and boiling points increase with increasing atomic number, which is why we start with gases and then we get down to iodine, which is actually a solid at room temperature. They're all diatomic, and again, melting point increases as we move down the group, and we'll learn more about that again when we hit chapter 11. Chemical properties, they have very high negative electron affinities. That means great or high electron affinities. They tend to gain electrons to form halide ions. They will react with hydrogen to form hydrogen halides, which we recognize from our basically almost all of our strong acids, and then HF, which is a weak acid, but it's a very strong weak acid. Fluorine and chlorine are more reactive than bromine and iodine. The higher up they are, the more reactive they are. And finally, group 8A, the noble gases. All are gases at room temperature, which is why they're called the noble gases. They're all monatomic. They have completely filled S and P sublevels. They have very, very, very large first ionization energies. Very difficult to remove an electron from them. Very high very highly positive values of electron affinity, which means it's very hard to add an electron to them, and that makes them exceptionally unreactive. We used to think they were unreactive completely, but now we know that the heavier ones like xenon can actually engage in some forms of chemical bonds with particularly reactive other elements. So again, there's that. Boiling point increases as we move down. Again, even though they're all gases, boiling point does go up as we move down.